Hello. We were looking at an example of application of stereo correspondence constraints to match the features, the lines from the left image to the right image. And I thought it would be useful just to talk about stereo correspondence constraints and a little bit more generality. And that's what we're going to do here. Okay, and where all this sort of fits in is really along this sequence right here. We've already found our features, and in order to do our triangulation to calculate the three-dimensional position of things, we need to have some sort of correspondence so that we can know the feature in the left image and the feature in the right image. And once we know that, then we can do the triangulation of where those corresponding features are to figure out the position of that point in the three-dimensional space. Well, so what we're going to look at is several different correspondence constraints. We've kind of touched on them a little bit already in the previous line matching lecture, but we haven't really focused on them. And the real problem is sort of emphasized right here. So I've got a set of lines or other features. They could be sift points like we've talked about. They could be little bits of edge points. They could be larger structures like circles or dots or corners or something like that. And we have a bunch of these in the left image, and we've got a bunch of these in the right image. And we're going to want to be able to match these together somehow, so like I say, so we can do our triangulation. Okay, and if we don't match them up correctly, then they will triangulate to a different depth position and give us the wrong three-dimensional result. Okay, so this is called the stereo correspondence constraint, or correspondence problem. And this is often considered the key problem of stereo. The reason being, once we've made the correspondence, given the epipolar geometry and the estimates, the projection matrices and things like that, the triangulation is really quite straightforward. Okay, it's the problem of actually figuring out which points do we want to do the triangulation with. And the general approach to the people doing stereotype work have taken is that we're going to have a set of different constraints that eliminate impossible matches. Okay, so for a given feature right here, like this little red line, we have a variety of potential lines in the other image that we could match with. And we're going to use some of these constraints to eliminate the matches that couldn't possibly be valid, and hopefully we'll end up with the matches that can remain, just be a unique match. So here's an example of one of these constraints. It's called edge direction. This could apply to sort of long edges like we've used, or long lines, or alternatively it could apply to small little edge fragments or sift features or something like that as well too, if you allow orientations in there. So here's a feature in the left image, sort of light on the left and dark on the right. And here are three potential matching features in the right image. And, well, this is an allowable match. This is not an allowable match because the edge direction goes the opposite. If you're going, say, light to dark, well, this is light to dark, but that's dark to light. That's no good as well. Similarly, the angle on this particular orientation where you go for sort of from the light to dark, that's the wrong angle. And again, we can say that's a bad match and eliminate matches that are potentially that have that property. So that's one, edge direction. Another constraint that one could use is edge contrast. So here's a little patch of edge right here. Here's the light side, there's the dark side. And what we're interested in is the contrast. So that's really the difference between the intensity values on the left and right. And here are three potential matches in the right image, and we want to look at those. And this one works okay. The absolute intensity values are different, but the contrast is about the same, so the difference between the two values. Okay, here the values are exactly the same as before, but the contrast is wrong. Here it goes sort of light to dark as you go from left to right. Here you go from dark to light. So that's in the wrong way. And here we do go light to dark, but the range is much too big. Okay, it just seems unlikely if your cameras are more or less set up the same, then that you would have that same sort of contrast. Anyway, so we're going to expect this kind of relationship, and those that don't match we can again eliminate. Feature shape, if you have features that are a little bit bigger, you can take advantage of the shape. We kind of going to take a little bit of advantage of this by saying that our lines have to overlap a sufficiently large amount, And that's kind of what we've got right here. Here's a line at a particular orientation. Here's 3 lines in the right image. This one's at a slightly different orientation, but it's about the right length. This one's far too short, that one's far too long, so we can eliminate those as potential matches. There's a couple of more generic kinds of constraints. One's called the uniqueness and the other's called smoothness. The smoothness is kind of straightforward, and except for you need pairs of features in this particular case. And what you're going to say that a surface is smooth if the depth values between nearby features don't change too much. And that happens if a surface is reasonably smooth. So if you have pairings that give you large changes in depth as you move from one feature to the other, then you can eliminate that pairing. Another constraint is called the uniqueness constraint. And normally, if you see a point on a kind of a regular opaque smooth surface, it can only possibly match one point in the other image. I mean, it's just there's exactly the corresponding point. There are cases where you might get none, and that's if an object, a feature point is near an occlusion boundary, so that in the three-dimensional world, the camera can see the point, and one camera can see that point, but the other camera can't see the point because it's hidden behind an edge, part of the three-dimensional structure. And it's also possible in some worlds to get more than one match if you have a transparency or wires or something like that. So you might have from one camera you might see 2 wires like this, but from the other camera the 2 wires line up. So you'd have one feature in one view matching 2 features in the other view. That's kind of an obscure case, and nobody really works with that sort of obscure case on a regular sort of basis. The final constraint that I'm going to talk about is what's called the epipolar constraint. And it's based on the idea from the epipolar geometry that we've been talking about. I've just sort of simplified the diagrams here a little bit. Here again is our 2 camera centers and our optical axes going out. Here's our 2 image planes. And I've got a feature point in my left image, and this is a projection of some sort of a 3-dimensional point, P, that lies somewhere along this ray R. Now, I don't know exactly where, using the information just from the left camera. All I know is from the camera center and that point in the image plane, that defines a ray, and I know that this point P has to lie somewhere along that ray. Well, if you look at the set of all possible points that lie along that ray and project them into the right image, then you get a line in the right image. So the lines project onto lines in the image. And this is going to be called the epipolar line. And since this point has to lie somewhere along this ray in the 3-dimensional space, that means any matching point has to lie somewhere along this line in the image. And that's really a great advantage for matching, because instead of having to consider matches between this point P and all 2-dimensional possible points in this image, we've reduced the matching territory down just to a single line right here. And we only need to consider points that lie on or close to that epipolar line. Okay, so that's the geometric intuition. We can do this kind of algebraically and implement it in a computer algorithm quite easily using our fundamental matrix right here. So if we have our point in the left image in our fundamental matrix, then the epipolar line is given by this E in the right image. That defines this line that we want to go across right here. And with that line, then we can look for points that are near that line, and they have to satisfy this constraint right here. If the 2 points are matched, you'll remember from the fundamental equation that the product has to be equal to 0. Or something very close to 0 because of image data. It never works out exactly as 0. So as I've said, this is great because it reduces effectively a 2-dimensional search problem down to a 1-dimensional search problem. And then we apply all the other constraints that we've just looked at to that 1-dimensional sort of search problem. Now you might say, well, where are these epipolar lines? And we can compute them sort of directly like this. But there's one thing that people do, and that's what they call rectify the images. Effectively, they apply a homography type transformation to sort out the lines so that all these epipolar lines turn into image rows in the image. So matching becomes even easier if it's on a given row in one image. In the left image, then as you look across in the right image, it's going to, the matching feature point is going to lie on the same image row. So it's kind of an easy transformation to do, and it's useful before you do your stereo matching. So if we look back at our matches that we've got using all these constraints that we've looked at before, we can see them illustrated right here. We're also going to kind of look ahead to do some of the matching calculations right here. So I've numbered the segments along right here. We can see the midpoints of those segments as being found. Not all the lines have found it. So this line right here, number 27, the midpoint is sort of off the edge, and that's because of the coincidental alignment with other structures that are in the image right here. So, but these are the correctly matched lines, and these are the correspondence between the two, by using all of these constraints that we talked about previously. So that's for the block that's in the lower left of the image. This is the block which is in the upper right of the image, and again you can see the corresponding sort of numbering of the lines, and some of these didn't match up for a similar variety of reasons. One of the matches that was a little bit surprising is that this line 92 did not match with this line 64, and the constraint that failed was actually the contrast difference. And the reason for that is if you look back at the original images, you'll discover actually these are sort of blocks with little white surfaces, and then there's a black line along the edge. And the consequence of that black line and the white surfaces is, in fact, the edge detector found several lines there, sort of an edge on the bottom side of the black line and an edge on the top side of the black line. So when the line detector found the edges, it looks like this 92 is on the upper side and 64 is on the bottom side. And when we did the contrast calculation, the contrast is sort of took account of some of like the dark pixels that are on the top side of the line right here and some of the light pixels that are on the bottom side. And the net result was the contrast just wasn't close enough to match properly. Right, so just a sort of short view of the kind of epipolar type constraint and some of the other correspondence constraints that we can use to make sure that we've got features in the left image that match properly with the features in the right image. These are not the only kinds of constraints, but these are the main ones that people use. And they don't work perfectly, but they do a pretty good job. I would say, about 95% of the feature matches that you're going to get you can be pretty certain that they are correctly matched. And once they're correctly matched, then you can do the geometry calculation to triangulate their position out into three-dimensional space. And moreover, this epipolar constraint that we spent a little bit of time talking about is quite a useful sort of technique, not only for constraining the matches, but also for giving us a quick sort of geometric algorithm for searching for corresponding points in the image. Thank you.